All right, welcome class. I had a question about how to do some problems on the notes as well as on the homework packet. And so I do appreciate these questions because it helps everyone out in this case, since I'm going to post a video and it's going to be good for this review since it's been about a few weeks. So let's go through these questions again. We're going to deal with the first one with Boyle's Law, which is that inverse relationship we see down here. Oops, here we are. Right here. And now we're going to translate this one down here, this equation, because we're working with this example of 53.2 milliliters at a pressure of 785 millimeters mercury. If all the gas is transferred to a new vessel with a pressure of 700 millimeters mercury, what is that new volume of the vessel? And so again, just follow that equation. P1 V1 equals to P2 and V2. We're going to follow this. Oops, what am I doing here? It's the pressure here. Here we go. So, you can kind of see a few things happening here. These two are our first values that they give us. Usually when they give you that, then you can say that's your first starting materials, your starting point. 53.2 milliliters at a pressure of 785 millimeters mercury. So let's plug that into our equation, because we'll find that the volume is going to be unknown here, but the pressure is going to be 700 millimeters mercury for the second pressure. So let's plug this in. So 53.2, we'll multiply that by 785 equal to some unknown V2 times 700 millimeters mercury. I'm only working with a mouse, so it's kind of hard to work with, but you can see this equation working right now because we have the second volume here to work with. And so to get this on its own side, we divide by 700 on both sides. Simple algebra. We divide here. What's going to happen is that cancels out, and it goes on this side now, 700. And so now the equation is just 53.2 times 785 divided by 700, and you should find your second answer, or your second volume. And I got a calculator right here. Let me just quickly do the math. We're at 59.7. 59.7 and volume in milliliters. So that's how you calculate it with that type of equation going on. Let's do another one. Let's do the one where it is Charles' law, the direct relationship between absolute temperature in Kelvin and volume. So we're going to use this guy here, V1 T2 equals V2 T1, and we're given three values already. So we got to find the fourth, right? Simple plug-in scenario, but something's different here. We notice that degrees Celsius needs to be in Kelvin for it to work with Charles' law. And how we do that again, if you take a look at the notes, we take that degrees Celsius, we add 273, and that's our units in Kelvin. So if I take 273 plus 25, I get 298. And if I take 5 plus 273, I get 278. So that's our answers in Kelvin. Now we can just plug it in simply as we see it, right? The 2-liter sample, which is our first volume, is collected at 298 Kelvin, first temperature, and then cooled down to 5 degrees Celsius, second temperature. Find the second volume. 2.0 times 278 equals unknown volume times 298. Alright, and then do the same process. We have to find and take V2 and keep it on its own side. We divide 298 on both sides, so the answer should be 2.0 times 278 divided by 298. And we find our second volume is going to be 1.87 units liters. So that's going to be for those first two examples for Boyle's and Charles' law, is that idea that we have to get it all on one side, keep the variable on the opposite side, and we find our answer. But just don't forget that we have to change Celsius into Kelvin when we're dealing with Charles' law. And it also it works for the combined gas law, right? So we have to have it in Kelvin, and the pressure can be in millimeters mercury, it can be in a number of pressures. So we didn't have an example for this one, but we worked with the packet on homework. So right now, I'm on the page for the combined gas law. And I want to do a problem with everybody. Let's do number 3. Actually, let's do 2 and 3. So it works for both of us. It works for everybody here. So it says 327 liters of chlorine gas is collected at STP. At what pressure will a gas occupy 150 liters if a temperature is 93 degrees Celsius? Now, to look at this equation again, is P1 V1 T2 equals P2 V2 T1. Let me put that right there. T2 P2 V2 T1. Okay. Now, I underlined STP. And the reason why I did that is because at standard temperature and pressure, the standard pressure is 760 millimeters mercury, and the standard temperature is 273 Kelvin. And so looking at both of these, we can translate these answers, or these numbers, onto our initial amounts. And so let's take an inventory here. What's the first volume? First volume is going to be 327, because that's what was given to us right here. Now, what's going to be the first pressure? Well, the first pressure is at STP, so we can say it is 760 millimeters of mercury. And the first temperature is also at STP, so we can take this answer and put it down as 273. Now, at what pressure will the gas occupy 150 liters if the temperature is 93 degrees Celsius? Well, we know our second volume is going to be 150 liters, and our second temperature is going to be 93. Well, we have to add 93 to 273. So, well, we have to add it to get our temperature in Kelvin. So we add 93 plus 273, and our new temperature is at 366 Kelvin. I got this answer again by just taking 93 and add 273. Now, what is that second pressure? Well, very simply put, we can just plug in all the values now because we have 5 out of the 6 values, and now we can use our equation. So, hopefully this doesn't look too terrible. Still writing with the mouse here. But let's put it all done together. We take the first pressure, 760. We multiply that by the first volume, which is 327. Multiply that by its second temperature, right here, 366. 66 equals, now we have a second pressure which we don't know, which we'll just say P2. Multiply that by its second volume, 150. And multiply that by its first temperature, which is 273 Kelvin. We have all the answers up here now. All we got to do is get P2 by its own side. And so what we can do is we can divide these two numbers over here. And so it'll look like this. 150 and 273. And these go away now. So now P2 is equal to 760 times 327 times 366 divided by 150 times 273. And so let's do that math. So 760 times 327 times 366. Okay, that's a big number, but if we divide that by 150 times 273, we find a different pressure. Now, pressure, P2, is going to be equal to 2,220. That's in millimeters mercury. So by taking this process and using the value STP, we can find this answer in millimeters mercury. Again, I do apologize for the bad, terrible handwriting, but let's continue on. Number 3. Now 3 is giving us all the values directly at once, which is very nice. So it says 0.00837 liters of nitrogen dioxide is collected at 57 degrees Celsius and 932 millimeters mercury. At what temperature will the gas occupy 0.224 liters if the pressure is 46.1 millimeters mercury? And so, let's list it all out again, right? First volume is going to be 0.0, oh my gosh, that's still too large. Okay. 0.00837. You know what? Everyone knows what this one is, right? I can just like label it on the thing. So this is V1, is collected at T1 and P1 here. At what temperature, so where is T2, if there is a second volume here and a second pressure here. Okay. One thing to note is that this has to be in Kelvin, right? So we take 57, we add 273. Alright, what number is that? 330. So there we go. Alright, now again, plug it in as you see it, right? V1 P1 T2 equals V2 P2 T1. So we take 0.00837 multiply that by its first pressure, 932. We don't know the second temperature, so we'll keep that as our unknown, equal to, in this case, our, where is it, second volume right here, 0.224 times second pressure, 46.1, oops, 6.1, and first temperature, 330. Okay. All we got to do is get T2 on its own side, right? So we divide these two over here and show it should look like 0.224 times 46.1 times 330 divided by 0.00837 times 932. Alright, let's whip out the calculator. 0.224 times 46.1 times 330. Divide that by 0.00837 times by 932. And I find a different temperature. T2 is equal to 436 Kelvin. And that would be your answer. Alright. Again, I do apologize for having the bad handwriting, but hopefully that makes sense. I will try to find a new way to get this writing format down, but that is so far currently what I have for homework and how to kind of deal and work with the homework. I may post another video down the road dealing with Avogadro's law and the partial pressures, but for right now, I hope you have a great day, and I really hope this helps. Thank you.